So the way I create Lewis structures is by using the dot-to-dot method. Alrighty. And I've copyrighted that. I make a lot of money off of this technique here. So first you want to construct your skeleton. You want to add valence electrons as dots. And then you want to connect the dots until each atom has an octet. All right. So let's take a look at HCl. All right. So we're given this formula HCl. So step one is to construct a skeleton. Now this is really simple. There is no real geometry we have to figure out about. So step one, construct your skeleton, is just going to be here's hydrogen, here's chlorine. Okay. Step two, we add valence electrons. So remember again, we look at the periodic table. Hydrogen is in group 1. We add a dot. Chlorine is in group 7. We add 7 dots. Okay. Step 3A and 3B are for charges. There is no charge in this atom or molecule or anything. Step 4 is to connect the dots until each atom has an octet. So here we go. We're going to connect this dot with that dot. So quite literally, like in kindergarten, you do dot to dot. All right. And then you analyze things. Okay. So the way you count electrons is as follows. All right. You identify all of the shared electrons that that atom has. This hydrogen has 2 electrons. So I say that it satisfies the octet. Technically, it has 2 electrons, the same as helium. So it has a noble gas electron configuration. Now, how about chlorine? Chlorine, we do the circle this way. We include all of the unshared electron pairs on the chlorine. Those are the dots that are left over. And we include the line there, which is 2 electrons. And we add them all up. Okay, within this white circle, there are 8 electrons. So we say also that chlorine has satisfied the octet. All right. So let's clean up this answer here. It looks a little bit weird with all these lines and check marks and stuff. It would look like this. All right. So that's your answer. Okay, hydrogen with a line to the Cl and then some dots. Let's do F2. All right. So here again, step 1, construct your geometry. There is nothing really hard to figure out here. You just put a fluorine on the left, fluorine on the right. Fluorine is in group 7 of the periodic table, so let's add 7 dots. Okay. Step 3A and 3B are for formal charges. We don't worry about that right now. Step 4 is to connect the dots until each atom has an octet. So let's try to do that. And let's stop, evaluate. We might have to make more bonds, but let's just look. So if I look at this fluorine on the right, it's got 2 here. It's got 2 from this pair, 2 from this pair, 2 from this pair. That's a total of 8. So we say that fluorine has an octet. Let's analyze this fluorine here. Okay, this fluorine has 2, 2, 2, 2. So that's a total of 8. And so we say that fluorine has an octet there as well. Let's clean this structure up. So fluorine has a bond to that fluorine, and we have to write in all of those valence electrons that have decided not to participate. Okay, so that would be the Lewis structure of fluorine. Okay, this is called a Lewis structure. If you want to call it the dot-to-dot structure, that's cool too. All right, how about NH3? NH3, as we're familiar with, is called ammonia. Okay. It's a gas at room temperature and pressure. It's used in refrigeration, fertilization, so on and so forth. Now, we have a complicated structure, so we need to construct the skeleton. When you construct the skeleton, you want to put the less electronegative elements in the middle. You want to put more electronegative on the outside of that. If there's any hydrogens, always put hydrogens on the outside. Okay? So we'll come back to ammonia, but I just want to talk about sulfuric acid. Okay? Now some students, they try to construct this. There's an H and an H, there's an S, there's an O, there's an O, there's an O, and there's an O. Okay? And this drawing right here is about as useful as a train that you could draw, and you know, it's just not going to work. Sulfuric acid needs to be constructed by looking at the periodic table. Okay? Who cares about where hydrogen is? That's always going to be on the outside of the structure. Over on the right, we have oxygen and sulfur. We're kind of familiar with the periodic table, right? Now, remember that more electronegative atoms are over here. En is my shorthand notation for electronegative. All right? Less electronegative is over here. Okay? So these ones are going to be in the middle. Okay? These ones are going to be on the outside. And we have a sprinkling of hydrogens on the outside of that. All right? So, sulfur, here's our formula, right? So our skeleton is going to be set up like this. We're going to have sulfur in the middle because it's less electronegative, right? It's further down in the periodic table. Surrounding the sulfur, we have 4 oxygens. Things are always going to be radial, okay? They're going to radiate outwards like a bicycle wheel, like a starfish, something like that, okay? So we have 4 oxygens around that central sulfur. And then we have 2 hydrogens, okay? Hydrogens are like corner pieces of a puzzle. And here we have kind of 4 corners, north, east, south, west, and you can put those 2 hydrogens anywhere you want. You could put one over here connected to that oxygen, or you could put one, say, over here connected to that oxygen, okay? So this represents a very good skeleton, all right? You don't want to draw a choo-choo train. Let's go back to NH3, okay? NH3 only has 1 atom here that's not hydrogen, so that's going to be in the middle. And then we have 3 hydrogens around that. So we spread them out, okay? Nitrogen, okay, so that's how we construct the skeleton. Step 2 is to add valence electrons. Hydrogen is in group 1. Hydrogen is in group 1. Hydrogen is in group 1. Nitrogen is in group 5 of the periodic table. So we want to put some electrons around that, 5 dots, okay? Then what you want to do is play dot to dot. You're always going to connect things to the central atom, okay? Nitrogen is the central atom, okay? So there's going to be a bond here, there's going to be a bond here, and then there's going to be a bond here, okay? And if you look at this structure very carefully, each of the hydrogen atoms have 2 electrons. So they have an electron configuration that's equal to helium, which has 2 electrons in the periodic table. So I loosely say it satisfies the octet. Okay? And nitrogen in the middle here is pretty busy, but let's very carefully count all of the dots that are within this white circle here. There are 8 electrons, so that means that nitrogen has satisfied the octet as well, okay? And that's a whole bunch of scratch work, just me explaining how this works and everything, but let's draw the answer here. Okay. All right, so that's the answer for ammonia. It does not matter where those 2 dots are left over on nitrogen, to the right, to the left, down, whatever. That just needs to be drawn there, okay? So that's NH3. Let's do water. And again, we're just doing some simple formulas here. Remember, we call this water. That's the scientific name for H2O. And here we just have oxygen, right? So that's going to be placed in the middle. And then surrounding that is going to be hydrogens, okay? You're never going to have a puzzle piece with two corner pieces connected to the middle, okay? Hydrogen can never be the central atom. Okay. Occasionally I have people try to draw the Lewis structure of water that looks like this. Remember that the formula for water has a 2 here, so that means we have 2 hydrogens, not 2 oxygens. Okay, so this is what we want to draw. So we start off by drawing oxygen in the middle, hydrogens on the left and right. Hydrogen has 1 valence electron, oxygen has 6 valence electrons. And then what you do is you make bonds, right? That's step 4 until you have an octet. Let's analyze the oxygen here in the middle. We can see that it has 8 electrons. Okay, so 8 electrons is great. Each of the 2 hydrogens has 2 electrons, so that also is satisfying what I call the octet, technically the duet rule, but don't worry about it. And let's clean up the structure. Water is going to have this formula here. I don't care if you draw it in a bent geometry or linear at this point, because we're not talking about 3-dimensional shapes of molecules yet. All right? So that in a nutshell is the Lewis structures, okay? And we can do that for any kind of molecule, okay? We can do silicon fluoride, okay? We could do CH4. We could do sulfur dichloride. We could do anything we want, okay? So let's just do some practice problems here, okay? Now, I urge you to stop the video, do this on your own scratch paper, see what you get, and then check what I get, okay? So let's do silicon tetrafluoride, okay? Silicon is less electronegative than fluorine, and these 4 fluorine atoms are going to surround the silicon. Silicon has 4 valence electrons, so we need 4 dots to start that off. Each of these fluorines has 7 valence electrons, and you need to draw these in, okay? You need to draw all of these in. All 7 dots on all 4 of those. And then you connect the bonds, and then you're done. Okay, that's the answer. All right, that's the answer. CH4. Carbon is also a atom with 4 valence electrons. Okay, and then we've got hydrogen. We have 4 hydrogens surrounding that central atom. And hydrogen has 1 valence electrons. And now we make bonds, and so that's the answer. Okay, that's the answer. So sometimes you have dots left over, sometimes not. If you use my dot-to-dot procedure, you'll never have the incorrect number of dots, because that's step 2 in my procedure. All right, here's this. Remember that the periodic table kind of looks like this. Chlorine's in the down here. Okay, so here's the part of the periodic table, and so remember that if you move to the left, it's less electronegative. So that's going to be your central atom, and then around that is going to be your more electronegative atoms. Sulfur is in group 6. So that's 6 valence electrons. 1, 2, 3, 4, 5, 6. Count them out. Chlorine is in group 7. So that's 7 valence electrons. Count them all out. And you have to add all of these dots. Okay, these dots are valence electrons. They're part of the Lewis structure. Now make your bonds. Okay, there's going to be a 1 there and 1 there. All right. And so that's going to be the answer for part C. All right. So did you get those right? I hope so. Let's now talk about double and triple bonds. Okay, double and triple bonds. And that's best just to illustrate it with some structures. So let's jump in. All right. Oxygen is always O2. Why is oxygen O2? Well, it must achieve the noble gas electron configuration, and that's why it is. So the first step we do is we make our skeleton, which is pretty boring here. Oxygen has 2, 4, 6 total valence electrons because it's in group 6. Okay. And we know that there's no formal charges here. We haven't even talked about that yet. So we skip to step 4, and we connect the dots until each atom has an octet. So if I share these 2 electrons here, it appears that the elements now have a greater amount of electrons than they started with. If I count, I can see within this white, I'm sorry, I messed this up. If I circle the shared electrons and the unshared electrons on the oxygen, I can see a total of 7 electrons. That's not 8, all right? That's not 8. So how do we fix this? We keep sharing. So grab your pencil and do another dot-to-dot line between 2 more electrons to create a second bond. Now analyze the number of electrons. Now you can see there's 8, okay? What do they should say in the Barney show? Sharing is caring or something like this? These oxygens, if they share more electrons, they can eventually get to an octet structure. We call this a double bond, okay? When you have 2 lines, that's called a double bond, and that consists of 2 covalent bonds. And remember that each line is 2 electrons, right? So that's a total of 4 electrons that are bonding those 2 oxygen atoms together. Okay, so there's a total of 4 electrons that are shared. 2 pairs, 4 electrons. Okay, so that's 2 lines. So that's a double bond. Okay, double bond. Let's look at nitrogen. Nitrogen is also diatomic. I wonder why. Well, it must be a molecule that contains an octet. So nitrogen has what? 5 valence electrons because it's in group 5 on the periodic table. Okay. And we just start sharing. Okay, so if we go like that, we count, we evaluate, all right, and we keep bonding until we get an octet. So there's 1, 2, 3, 4, 5, 6 electrons. Well, that's not enough. Let's do more. Okay, let's count. Now remember, whenever you count, you're counting the shared electrons and all of the leftover unshared electrons on that atom. So that's what we're doing. So 2, 4, 5, 6, 7 electrons. So we're almost there, 7 electrons. Wow. Let's keep going. Okay, now what do we have? We have, okay, we have 2, 4, 6, 7, 8. Now we have 8 electrons. So let's clean this structure up. It looks really weird here. 1, 2, 3, nitrogen. Leftover lone pair on the right, leftover lone pair on the left, and that's nitrogen. And we call this a triple bond. Okay, a triple bond. So sometimes molecules are held together by single bonds, sometimes double bonds, sometimes triple bonds, and sometimes a whole combination of things. Okay, so oxygen is in the Earth's atmosphere. Nitrogen as well makes up 80% of the Earth's atmosphere. Why is it so much more prevalent in the Earth's atmosphere? It's less reactive because that bond is very strong. Whenever you have a triple bond, that is going to be a stronger bond than a double bond, okay? And we'll talk about bond strengths briefly later on. CO2 is our next molecule. This molecule is also in the Earth's atmosphere. And remember how we construct our skeleton. Here's our, a brief snippet of the periodic table. And we see carbon is right here. Okay, it's further to the left in the periodic table, which means it's less electronegative, and we place it in the middle. Oxygen is further to the right in the periodic table. It's more electronegative, so we place that outside. Okay, and I don't care if you draw this in a line or bent or whatever. Carbon has 4 valence electrons. 1, 2, 3, 4. Oxygen has 6 valence electrons. Okay. And we want to draw some bonds now. So at least everything has to be connected with one line. Now, if you look at the oxygen on the right here, it only has 7 electrons, okay? 2 from the bond, and then 3, 4, 5, 6. I count only 7. So what we need to do is create another bond, okay? Create another bond right here, okay? And now that oxygen atom has 8 electrons, okay? And we do the same thing with the oxygen on the left. It only has 7 electrons right now, so let's make another bond. And now this oxygen on the left has 8 electrons. Let's clean this guy up. Oxygen, double bond C, double bond O. Okay, so that kind of has a very interesting structure. So that's carbon dioxide, all right? So this is the cleaned up structure. How about C2H2? Okay, now this molecule has more than one central atom, but when you're dealing with organic molecules are comprised of carbon and hydrogen. Think about where carbon is found on the planet Earth. Carbon is in coal mines, it's in the middle of the Earth, and so it's in the middle of molecules. So when you start out, put all your C's in the middle, okay? Now where do you put these hydrogens? You could put 2 on the left, 2 on the right, or 1 on either side. The correct answer, that won't get you into stumbling blocks, would be like this. Let's add our valence electrons, H, 4 4 valence electrons for group 4 elements. And let's draw some bonds. So we'll do that in green, I guess. So here we have to have at least a bond between each of the elements to combine them, right? To make them held together. So hydrogens are great. They have 2 electrons total, and these carbons are not okay. They have only 6 if you look. Let's make another bond. Now it has 7. Let's make another bond. Now it has 8. So let's clean that up and write the answer. This molecule is called acetylene. It's used in welding and auto body work. And that's the answer there. So there's no dots left over. There's a triple bond in the middle of the molecule. And there's a single bond on the ends. Okay, so it's, a combination of things there. Okay. So for very simple molecules, we can write the Lewis structure by just pairing up the unpaired electrons on the substituent atoms, okay? And that's what we've been doing, okay?